Right, so this lab is the 2-week lab. Okay, still November the 6th. So if you look at the mux, it's a 2-to-1 mux. Okay, it's different from the one we derived from the truth table. This only has 4 transistors, way smaller than that. We prefer this mux instead of the traditional mux from the truth table. And it could be very interesting because if you connect it this way, all the drains and sources are being used for the signal transmission. So where should you connect the VDD and ground to? It's like you got a device and you don't need a getting the power? Seriously? There's no power. If there's no power supply, it shouldn't work, right? Usually. But do we really have power connections in this schematic? And where? No. No, these are just the pins, right? That's a chip, and these are the input outputs. It's not power. But do you have power somewhere else? I forgot if you don't include VDD and ground, if there will be any issue with it. There might be. That's probably why I have to include VDD and ground over here, but didn't connect them to anywhere because you don't have the connection to it. Okay. Or there are some connections, but you cannot see. So for all these PMOSes and NMOSes, how many terminals do they have? How many terminals do they have? Remember? Is there any connections are not being drawn here that actually physically connected? All the devices are 4-terminal devices. It only shows 3 terminals: drain, source, and gate. Where's the body? Remember the N-well tap and P substrate tap? So there's another connection with it, right? In the LT SPICE, we usually have 4 connections, 1 pin in the middle that we connect to the VDD for PMOS and connect to ground for the NMOS. So it's a well contact, okay? This one, these transistors, they all have a well contact, but it's just not showing here. Remember in the very beginning, there was a setting, I think probably in the preferences, you already hid the 4th terminal. It's not there anymore, but actually exists. If you look at the layout, you do have it here, right? That's the body. That's how it passes LVS or NCC. So you do need a body contact. However, the schematic is trying to make it simple and looks cleaner. That's why it's not showing that the middle pin as a body contact. So the PMOS's body contact is physically shorted to VDD, but it's just not showing here. And NMOS's substrate is shorted to ground, but it's not showing here. Okay, so you do need a VDD and ground pin to be placed. It looks weird. It's placed in the schematic, but not connected to anywhere. So these ports, there are just 2 ports that I know in electrical VLSI. They are called off page or off the page ports. Maybe off page ports. So which is VDD and ground. So if you placed them in this lower level schematic, and it's being recognized in the higher level as well. If you wrap it up in a mux and you create another schematic, keep in mind, it's a very important concept. If you create another schematic like this, all right? So for example, this mux has VDD and ground, these 2 symbols in it, okay, which is this symbol. And you have the inverter has a VDD and ground symbol in it. It's like you have these are
lower level schematics, right? Has a VDD symbol, has a ground symbol, has a VDD symbol and ground symbol. And these two ports are off-page ports. It's different from other ports you include in the schematic. So if you go to the library on the left-hand side, you see some of the ports look like this, right? These are also ports, but these are not off-page ports. They cannot go beyond that level of schematic. It's just within that schematic. However, if you put a VDD and ground here, right, you get another schematic on the top, you wrap them up as a chip. Okay, you just grab all these two schematics or symbols into the higher level schematic. These VDD and ground are actually being recognized in this layer, and they are shorted to each other. Keep in mind, if you put a VDD and ground in here and in here, and you use it in a higher level schematic, they are shorted. But for these ports, they're not. If you put it in the higher level, they are just hidden in that schematic. You have to rename the port, whatever you want. Which makes sense, right? For example, you are using a AND gate, okay? And you name it A, B, C, okay? And in this higher level schematic, you are using like 10 of these AND gates. Do you want this layer of schematic recognize the ports A, B, C or not? No. Why?
So there'd be a million things.
No. So what if you have, for example, you are using 10 of these here, right? This is a lower level schematic. You are reusing the symbol in the higher level schematic. However, these ports are being recognized in here as well. So they are being recognized as ports. We have 10 of them. What's going to happen? 10 of these ones have the same name of ports. What's going to happen? All the A's are sorted together. All the B's are sorted together. You want that to happen, right? Sometimes they have different inputs and outputs. Okay, so don't want these ports to be recognized over here. Okay? They should be hidden in the schematic, in the symbol. However, these two are different. Keep in mind, that's the difference. If you use it in the higher level schematic, VGA grounds are either even they're inside the symbol, but they are recognized as ports, off the page, which means it's off the page. It's not within that page or the layer. It's go beyond that. That's why we put a VDD and ground over there. So if we reuse the mugs in the higher level schematic, the VDD and grounds are being shared with the inverter's VDD and ground. They're using the same VDD and ground. Okay. So do need this because you don't have any physical VDD and ground connections since you are not showing the body contact, but it looks weird, but you still have to place them over here, okay, to make it pass any root checks. And these, okay, so in the inverter for the selection, it's a 2-to-1 mux, so it's either S or SI, right? S is 0 or 1. It's just one bit, right? S or SI. You can manually draw a schematic of the 8-bit mux. So the 8-bit mux is passing a bit or passing a byte. So you can choose in between 2 bytes, which byte you want to pass it to the output. Okay. Make sure you have snapshots of the error checks. Should pass, no error, 0 errors, 0 warnings. Okay, problems here. So for the layout, it's also very interesting. There's no physical connection to it. There are physical connections to it. So when you are laying out the transmission gate, what's going to happen? What's really happening here? If you look at
there's no like VDD you directly connect to VDD like the inverters, right? Connecting up to VDD, but you still need these two connections. But you didn't draw a wire. What's really happening?
Like the P substrate and the N.
Yeah, they are shorted where? From where?
So what is this? So these are PMOSes, right? So what is this? If you draw it in a cross section of it, what is this guy?
And P is going down.
Is that right?
Yeah, because it's the light green color. It's the same as the gate.
And X.
Oh, wait.
Well, it's a well. It's a well contact, right? So it's you see these are both dots, so they match, which indicates that they are being built in the same well. Okay, so these are PMOSes, no doubt for that, right? PMOSes. For these guys, right? So PMOSes are built in what? In what? So what we are really trying to do right here? What we are doing we are always connect the NOL to the high potential in the circuit. Why? Because PN junction is a diode, right? Okay. I don't want to forward bias the parasitic diodes. I want to hook this up to VDD, so you never get current running through the diode. It's not a desired diode. It's just intrinsically unintentionally you built over there, right? These are diodes. These are PNs. Okay? So we want to connect the N body to the high potential of the circuit always. So you never forward bias the diode. So what we want to do for the N well over here. You implant N plus over here, this highly conductive, and we short this one to VD. Right? Okay. So that's the N plus material in N well. For this guy, the N plus material in well. Okay, and the background dot is N well. So after you make it that size or shape, you're gonna move it closer to the PMOS, so the dots area kind of overlap with each other. It's basically like this, right? You got PMOS. The PMOS is originally in the NOL already. You don't have to do anything. You grab a PMOS chip or PI. It's already in the NOL. Okay, that on top is an N plus material in the NOL. Right? And these are the dots. You want to move them closer until they overlap with each other. Okay, they overlap, so they are building the same NOL. Okay, so if you connect this to VDD, and this NOL is being short to VDD as well at the same time. And that's what we want to do. Make sense? Same for the NMOS. It's already the P substrate. It's just assuming it's not. Trying to keep it consistent. But you do need a P plus over here. So the same concept, right? So NMOS, since we don't have a well, so NMOS is directly being viewed in the P-type. P-sub. So we are treating P-sub as a well. And that's a P plus material, right? In P-sub. It has a dashed line and a P-sub, okay? You still have to move it close to each other until the slashed area overlap. So we assume these two are being built in the same well, which that's the substrate. This is a very simple make keep them close enough. Let the slashed area overlap, so it's not the EDA tool is not recording errors. But basically, they are always in the same substrate. They're not changing anything. Just move it close enough and let the slashed area overlap. So the EDA tool is not recording errors. Okay, but you don't have any physical connection to it from a transistor. You don't need that. We just need a physical substrate from the body to be overlapped. But you don't need any physical connection. If you look at the cross section of the wheel, there isn't any connection in between the transistor and the well contact. It's just a well overlap.
And I highly recommend you guys don't looking at or staring at my layout and duplicate it. Try to do it yourself from the schematic instead of copying from the layout. So it's not helping anything at all. Okay? You're not gaining any skill just by duplicating the layout, the drawing here. It's like an art class, art 101. It's not even that beautiful. It's just electrical traces. Don't make it art class, okay? Thinking about connections and the traces, overlaps, short circuits, whatever, and then start debugging from that. Okay, so the yellow trace is a metal 3. Okay, I think I did it that way is because it must be a reason there. I probably have to, these are all the as a result from my experience, right? When I was trying to draw it, I find out I have to do it that way. But if you design it yourself, you may find a better way, get the trace out from the layout. The reason that I have to get a connection out from the layout in the middle is this is an 8-bit mux, okay? So I need the ports from the outside of the block. So I put it below the block, but you can place it on the top or anywhere else you want. Okay. These are simple enough. So see, I had Y's. So the Y's are obviously output, and the 2 inputs to the transmission gate, the A's and B's, okay, at the bottom. A0, A1, you can see. And so A's and B's are at the bottom. So 8-bit is a 1 byte input for each port. Okay. So 2-week lab, so I think this week, if you can finish the 8-bit layout of the transmission gate, that will be good in the lab. If you still have time, you can keep moving on to the high-speed full adder. We have the schematic and stick diagram drawn in the notes of the lecture. If you go back to the lecture, I believe it's last week, you should be able to see the stick diagram. So highly recommend that you guys design your layout from the stick diagram instead of staring at my layout and duplicate it. Okay, so got a schematic in here first, run the DRC check, run some simulations to verify this is the full adder logic, and then you can start doing the layout. Okay, make sure schematic is correct. That's critical. Make sure it's doing a full adder logic before you move forward to the layout. Okay, and you can see for the first one, I think that is C for C out. Okay, for C out, carry out. I'm showing you that you can draw the layout by looking at the line vertically. But it's not the way that we have been doing in the class. I think it's still better to use stick diagrams. I think I drew the stick diagram in the class. You can refer to the notes to find out the stick diagrams. It's not that difficult. I think you guys have been trained in that extensively, so it should be easy to figure that out. So I didn't use C diagram for this one, okay? But I did it for the next one, like this, okay? All right. That's the final layout of the 1-bit flatter, the high-speed flatter from the AI logic and stick diagram. So this saves a lot of space compared to the traditional one. So you know the logic of the flatter, and if you draw it using standard logic gates, okay, it looks like this. You have done that in the past few weeks, I think. It's pretty big. It has all the individual logic gates. If you use the AI logic and stick diagrams, it becomes this. It's the same logic, but you can see it's probably 3 times smaller than the original, the traditional one. Okay? And it does the same thing and even faster. So you know the benefit of using AI logic and the stick diagram to design logic circuits instead of using the standard logic gates. It's a huge difference. And this is a simulation. Okay, so I wrapped up that flatter into a symbol. Okay, one is 1 bit, another one is 8 bit. Wait, I don't know what's the difference here actually. High, low. Anyway, you'll figure that out. It's just a simulation from the schematic you just drew and lay out. And then put signals in here. You don't have to verify every single logic. I just run a few of them, and if they all work, it's 99.9%. It's a good flatter. Okay, and then place all the flatter into one schematic, so it becomes 8-bit high-speed flatter. Make sure it passes all the ports and topology and size check. And that's it. Okay. So that's the second last lab we're going to work on, and the last one will take another 2 weeks. It's also a lot. And after that, I'm gonna add a few other labs of using cadence instead of just stopping here. I think we have probably 2 or 3 more weeks after lab 9. Okay. So I'm gonna give you access to the server and run some cadence labs as well. Okay.
How does the server work? Do we have to use the computer in your lab?
No.
Okay.
No, you can connect through the Wi-Fi from the laptop. All right, any questions? No?